Welcome back to the workshop. We want to continue taking a look at section 3.7, conditional distributions. And what we'd like to take a look at in this video is another situation where we have more than one random variable, or sorry, more than two random variables under consideration. And essentially what happens is we can restrict our viewpoint or as much or as little as possible. So what I can do, if I want to find the conditional probability or the conditional distribution where one particular variable takes on one specific value, I can do that by saying, all right, let's take a look at these other variables given that this one is that value. Or what I can do is I can say, hey, let's let these two variables take on their specific values and then look at the distribution of this one remaining variable. So that's what we want to take a look at in this example, and really just one of those situations, but it generalizes so easily that I don't think that there's a lot of explanation needed, but certainly at least an example. So let's take a look at such an example. So we considered this joint probability density, or this joint density function, in our last section. And what we found was, let's see here, I believe we found a joint marginal distribution. That might be correct. And what we'd like to do this time around is look at things a little bit differently. So we want to find the joint conditional distribution. So it's called joint because it still depends on two variables after we essentially remove or give a condition for one of the variables. If we were to give a condition for two of the variables, then what we would be left with is, what we would be left with is just the conditional probability or conditional density of one particular variable. So in this case, again, three continuous random variables, and we want to look at this joint probability density and find the conditional distribution. So for the conditional distribution, it's just a matter of dividing by the distribution of the functions where they're given specific values. So what I'm saying here is p of x comma y given z it's always the density function f of x, y, z, or f of x, y, or f of x, y, z, w, or however many variables there are there. It's always the joint density divided by the marginal. So since we're looking at given z here, I just want to find the marginal distribution of z. If it were given zw, I would want to find the joint marginal distribution g of zw, and so on. So in this case, since we're looking for this, the first thing that I actually have to do is find the marginal distribution g of z. But the marginal distribution g of z is just a matter of looking at all the values, considering all values for x and y. So x and y range from 0 to 1 and 0 to 1, and it's 0 everywhere else. So although I should integrate from negative infinity to positive infinity for x and y, I don't need to because it's 0 everywhere besides 0 to 1. So this is the integral from 0 to 1 of the integral from 0 to 1 of 1/3 times 2x plus 3y plus z. And again, the variables that I'm getting rid of here are y and x. So let's do dx dy. I think that's the order that they typically present it in here. And certainly the integration bounds match that yet. So let's perform this integration. You could do this quite easily yourself, or you could ask Mathematica or another computer algebra system to assist you. And you would find that this is 1/3 times 1 plus 3y plus z. Integrate with respect to y next. And then again, you should be capable of performing this integration without any issues. Again, 1 is a constant, z is a constant because we're integrating with respect to y. So keep that in mind. And then we would have that this is equal to 1/3 times 5/2 plus z. And the reason that I wrote it this way, 1/3 times something, is because we're going to find a quotient here, and f is expressed as having a coefficient of 1/3. So having that pulled out front means I can do a little bit of simplification. So maybe you find something different or prefer to find something a little bit different, and that'd be okay. But this is good as well. All right, so that tells us that f of x, y given z is equal to f of x, y, z divided by g of z. And this is defined for, if we take a look here, g of z, this gives us z values between 0 and 1 because it's going to be 0 everywhere else. So we're always looking at z values between 0 and 1. Keep that in mind. So then we have f of x, y, z is 1/3 times 2x plus 3y plus z divided by 1/3. 1/3, try that again here, 1/3 times 5/2. 5/2 plus z. And what this is for values of x which are between 0 and 1, values of y which are between 0 and 1, and values of z which are between 0 and 1. Once we choose a particular z value, then that gives us the conditional distribution of, the joint conditional distribution of x and y given whatever z value we let z be. So some simplification that we could do here, of course, get rid of the 1/3 because they'll cancel out, and we could leave it just like this. If you wanted to, you could multiply by 2 to get rid of the fraction here as well. I'm not too worried about that, and I'll let you do as you please there. And the last bit, or the second bit, of course, we can end up with still a value of 0 for our density function here. And we're always looking at z between 0 and 1. So I don't want to simply put otherwise here. That's not going to actually make sense because this is not defined or should not be defined for z values outside of the window 0 to 1. So this is for several collections of things, right? This is for x less than or equal to 0, or x greater than or equal to 1, or y less than or equal to 0, or y greater than or equal to 1. Okay, and I make no reference to z because it's undefined where z takes on those values. And I don't have to specify that because it's undefined, right? I haven't defined it, so it is. All right, but that's exactly it. This is the joint conditional distribution, or density rather, of x and y given z. Again, I could choose a particular value of z, and that would be my specific conditional distribution. All right, but that's it for this video. So we'll move on to one more example, one more definition and example, where we're talking about the independence of continuous and discrete random variables, which also is very similar to what we've considered in the past. So I'll see you guys back in the workshop very shortly.